Good morning, everyone. Can you guys hear me? All right? Okay. So, good morning, everyone. I'm DB. First of all, thanks for the organizers for inviting me to this conference. All right. Thank you. So, today's talk is going to be about from code to compromise, where we look into how we can take IDE like VS Code or WinSurf and turn into a very reliable initial access vector targeting developers. So a bit about myself. I'm a researcher and malware developer at Black Hills Information Security. Previously, I was a consultant with companies like Certus and Palo. I do a lot of open source tool development. You can follow me on Twitter and GitHub. That's my iterate. And when I'm not working, I'm big video game nerd with like also movies and stuff. But let's get to the problem. So I like to start with a little bit of an exercise here. In the next two slides, I'll show you one legitimate extension downloaded from a store and one which has been backdoored with some malicious code. And let's see if you can spot the difference there. So this one is coming from WinSurf. This is a live preview is an extension by Microsoft. So can anyone tell a difference between which one of these might be malicious? Nope. Let's move to the next one. Let's see if VS Code does any better. So now these screenshots have been grabbed from VS Code, and you might think that, hey, this is Microsoft extensions in a Microsoft product, and we have the blue check mark, but can you tell any difference? So hopefully by the end of the slides, we can create one of these malicious extensions ourselves. So let's talk about let's look into the brief outline of the talk. So first we'll look into a bit of VS Code, its history, along with some other popular IDEs which have been based off VS Code. Next we'll look into attacks in the wild, some malicious extensions which have popped up over the last year and have targeted developers. Third, we will do a bit of I like to do this called a maldev walkthrough, where we start from a simple hello world program and we build one of those hidden malicious extensions, and finally we'll look a bit into the detections and IOCs for such attacks. So moving on. So VS Code I don't think needs any introduction. I'm pretty sure a lot of people here already use VS Code. It's the world's most popular developer IDE. Just a bit of background still, it's been around for 11 years. Now there are two versions of VS Code. One is the open source version, which is forked by other popular IDEs, and then they put their AIs on top of it. And then there's the official release, which Microsoft brands with its own telemetry and a bunch of stuff. The most important thing to note here is that it's built on top of Electron, and why this is important is because Electron poses a lot of restrictions on what you can and cannot do. This has been especially relevant since Electron version 20, where they made a bunch of changes to how they deal with memory and stuff. And finally, it has supports extensions, which we're going to talk about. And another very important thing is VS Code does something really interesting, which is it offloads each of its tasks to its own processes. So you might think that other IDs might divulge one task to a thread, but VS Code does it at a process level. So rendering is controlled by one process, loading extensions is controlled by another process, and so on. So why target VS Code in particular? Developers often have a lot of API keys, secret tokens and stuff which can be really useful. They have some privileges and often they are excluded from EDR environments. So targeting VS Code can be an amazing, can be really rich and help you escalate within environments, as well as if you have developer credentials, you can not only gain access to prod, you might even get access to secret keys and stuff like that. So let's talk about the rise of coding agents. And over the last 2 years, AI has taken over. We have seen so many things come out. We have WinSurf, we have Cursor, we have a bunch of other AI-powered platforms. But more or less, most of these are powered off VS Code. So what can go wrong here, right? We have some amazing AI agents built into your IDEs, which can help you code 10x faster. So as Uncle Then one said that with great AI editors comes marketplaces which are not heavily monitored. And what do I mean by that? So due to certain legal reasons, Microsoft told these other editors which forked off VS Code that, hey, you cannot use our extension store for your product. So what happened is that they created something known as OpenVSX. Those who have worked with WinSurf or Cursor, they know that in order to install an extension there, you have to install it for OpenVSX. But the problem with OpenVSX is, since it's not as heavily monitored as Microsoft is, it has been led to some attacks, some extensions getting compromised, and we will see those some attacks in the next slide. So in this talk, we'll mostly go over these 4 attacks. One where we will look into Solidity extensions, which were extensively targeted. Next, we'll look at this something called malicious corgi, which was AI code writing helper, which exfiltrated all your data. We have 2 versions of the Glassworm malware family, and they both do very interesting things on their own. So let's look into the Solidity extension bonanza. So before we look into Solidity extensions or what, it's very important to know what this repository is. So this repository by this guy called Juan Franco, it has been around for 10 years, and it contains an extension which is very popular and really very helpful. If you are a Solidity developer, you'll find that it has syntax highlighting, it does a lot of compilation for you, and as you can see, it's very popular. It has 10 million downloads and 1.78 million installs. And like crypto developers love it, so do attackers. And what do I mean by that? Last year, Kaspersky found out this particular malicious extension in the wild, which was responsible for stealing $500,000 from a Russian crypto developer. And right now you may see that, hey, it looks a lot like the extension. If you do a side-by-side comparison, you can see how well copied this is. And in this enlarged view, it might look like, hey, there are significant visual differences. But when you are installing it from the cursor prompt, you can see that it's very difficult to tell them apart. And the attackers in this case, they were able to mangle with the download counts or the SEO, and somehow if you used to search for Solidity, this extension outranked the original extension. So let's take a look at the code, what is happening here, right? So this was the malicious extension code, and honestly, I don't understand normal JavaScript well enough. I won't be able to comment on obfuscated JavaScript. But at the very end of this program, there was this snippet. Now, there are some interesting bits here, like why is Solidity and Solidity extension checking my platform, and also why is PowerShell there? And you can see bits of the famous PowerShell execution policy bypass statement, and we are seeing that it is fetching a file. If we beautify this code a bit, we'll see that it's essentially a very bad obsec, and they're just downloading a PowerShell script from the internet and executing it. So we'll not dive into the what the PowerShell script is doing, but mainly focus on the delivery. And I would say this is very bad obsec. But there's another one. This developer tried to propagate another malware using the same techniques, but this time they did something really interesting. So in the original extension, the author's name is Juan Blanco with a small l. What they try to do is they try to go around that by replacing the small l with a capital I, which in the if you look at the cursor extension page, it looks very similar because of the font they use. So they did not give up. So right when you think that, okay, maybe that's it. Those are 2 Solidity extensions targeting malware targeting crypto developers. There's another one which came around. And this time, at least the malware developers had a sense of humor. It's called Sleepy Duck. And this did something really interesting, which is that it uses the whole VS Code extension to establish C2, but over blockchain. And the advantage of that is, you cannot kill a blockchain. You can, let's say, if you have a C2 which redirects to a domain, you can take down the domain, but not the blockchain itself. And again, they use the same tactics, more or less. They use the same Solidity name, they use the same logo. This time also they tried to copy the developer name, but they put just a dash or a hyphen between the names. So, and another really interesting thing which they did is, initial push of this extension, when it was first published on October 31st, they did not make it malicious. So when they were initially scrutinizing this particular extension, they were like, okay, this is good to go. But on subsequent updates, that's when they pushed the malware. Now, this does your pretty standard enumeration stuff. Those of us who have been into malware development for a while, these tricks like getting your MAC address or like getting a time zone and checking that. Those are very common tricks for things like sandbox evasion. And for example, if there used to be this trick where we used to check before execution that, hey, is this MAC address corresponding to a VMware workstation or a VirtualBox machine, or is the timestamps time zone set to UTC, because those were the usual indicators that, hey, this is being run in a sandbox. So it does that, and then what it does is it sends it to it makes a post request with all the data and waits for the server to revert back, and then it executes it if the server responds with certain parameters. Now, they also, you can see, you search for Solidity, you see these extensions again pop up. And there have been 14,000 downloads. We do not know how legit those downloads were, but again, it's very difficult to tell these two apart. And not only that, this developer did not give up. They published several of these extensions with some variation of the name Juan Blanco, as well as like the Solidity logo and stuff to fool more crypto developers. So there has been a very targeted attack against crypto devs. But as Paulo Coelho says, that everything that happens once can never happen again, but everything that happens twice will sure happen a third time. And we've already seen 3 extensions, and these are all the other extensions which use the same trick to target developers, cryptocurrency people. And you can see it's a bunch of the combination of the original extension name plus Solidity in some way or the other. Now let's look into something else, malicious coding. Right. So initially we saw the rise of like AI-powered coding, and there were a bunch of extensions which provided this feature that, hey, here is a extension, it will help you write code and stuff. So this was one of those extensions, ChatGPT slash GPT MOS. They promised that, hey, we will, what we'll do is, we'll take your code, we will run some AI stuff on it, and we'll help you write better. That was the promise. But let's see how the promise goes. Now, again, looking at the source code behind this extension, this doesn't look like it's doing any AI stuff. So let's break it down into little sections. So if you look at the first section right here, what it is doing is the extension was reading all your files. And whenever you used to open a file, there was this particular function was triggered, and it read your entire document and it base 64 encoded it. After base 64 encoding the whole thing, it used to send it to a hidden iframe with all the data, and the iframe was sending the data back to some servers, essentially exfiltrating your entire file. Not only that, every time you used to make any changes to the a code file, a source file, an environment file, it used to do the same thing. And not only that, it had this, the server sometimes used to send messages back, and it had a function to handle those messages. And one of the interesting functions here is, whenever the server sent a response with get file list, it will call this function called get files excluding getting unit. So what it did was, if we look here, this iterated through your entire directory, read every file and exfiltrated it back to the server, which is, this includes your secrets, this includes all your sensitive code files and everything. Not only that, another scary thing it did was, it had a hidden iframe that whenever the extension was loaded, it would redirect to a page called ChatMOS data tracking. This was the link of the page. And that extension, that link loaded 4 very different profiling tools, so that your profile could be like you can draw correlation between which developer is writing which code. So this was a very targeted campaign as well, which is delivered through another VS Code extension. But so far, all these detections have come down to a very simple thing, that can you read code? Like if I give you this code, beautify it a bit, you can say that, okay, this looks malicious. This is where the genius of the first Glassform code comes in, where it was self-propagating malware. But the interesting thing about it was, if you look at this source file, what's there? There's absolutely a big blank part. So if you look at the source file, you might think that, hey, this whole thing is empty. But it turns out it was not. It was, the source file contained encoded data in such a way that it was the editors were not able to render the data. So so right here there is Unicode encoded data, and the researchers at Code, they said that who uncovered this, that hey, the data the big blank you see here, it's not obfuscated, it's not encrypted, it's just encoded using Unicode characters, which you cannot see. And this affected a bunch of these extensions, which led to a very big malware campaign. Right? But Glassform wasn't done yet. Glassform came back with a round 2. And this time it came back as this particular extension. Not like this was the most famous one, was the icon theme material. So icon themes are a very popular theme used on VS Code. I used it for a very long time. And they again tried, this is the hallmark of most malware or extensions, where they try to copy already existing or already well-known extension. And as you can see, one is material theme icon and another is icon theme material. So with very similar names, but this one is malicious, that one is not. Right. So let's look at the source code. This is essentially what the entire source code did. There's some interesting things to point here, is that it checks the malicious JavaScript, it checks your operating system that, hey, what is it? Is it Windows or Mac? So Linux uses receive from this particular one. And on Windows, it loads something known as a os.node binary. And on Mac, it means a darwin.node binary. Now, is anyone familiar with .node files? Show of hands. Right, we have one person. So we'll get to .node files a bit down the road. But this is something which we can load up in IDA. So one thing which I would like to point out before we jump into that is that if you look into the virus total graph, you'll see that in the execution parents, it says a zip file. This is something we'd like to keep in the back of our heads, because this will come into mind, like why it's mentioned zip specifically. But again, those node files, as we'll see again a bit down the road, that is something you can load up in IDA. And it has a bunch of malicious strings with secret keys and stuff. You're not getting into that, that's a separate talk on its own. But the most important thing is, if you remember the first Solidity extension which we discussed, the one with obfuscated code and which we called out on the bad offset, it had PowerShell. It was just calling a PowerShell script which anybody can take a look at and it would be suspicious. But we ended up using IDA Pro. So we had PowerShell script, from there the next extension used JavaScript, the next extension used Unicode, and finally we have to go native, which is an improvement. So let's think about that. That from something so simple, we went to something so complex. So anytime I have to open up IDA to do something, I will classify it as pretty advanced stuff. So looks like going native is where the fun begins. So that's what we are going to do here, right? So why worry about native code? So if you're running from in the JavaScript context, it might be very difficult to do certain things. For example, if you want to establish your traditional C2, you want shellcode execution, or you might want certain OS capabilities, you might want to call OS APIs. doing that from JavaScript can be a bit difficult, especially after Electron 20, when they put certain restrictions on what Electron processes can do or not do. Right, so that's one reason why we might want to use OS APIs. And another thing which I have found as a malware developer is, since most of the techniques are like POCs which we have, they're already written in C, C++, Rust. Transporting that into JavaScript FFI might be a bit difficult. So having that support for native code might come in handy there. And as in general, native code is more difficult to like reverse engineer something compared to a JavaScript, though that is subjective. But again, it's easier to like read a file than open up IDEA and analyze it. So that's what we are going to do next. So where does that bring us? We are going to use something called node add-ons. Now, yep. Okay. Yeah, so let's look at the definition of node add-ons. So this, according to the official Node.js documentation, it says that add-ons are dynamically linked shared objects written in C++, and you can essentially use them, like you can require them in JavaScript like we do with other JavaScript modules. And there are multiple ways to implement add-ons, and we would be sticking with Node API for now. So JavaScript and C++, I'm not a fan of either of those languages, and like to me it's really painful taking two languages which are so wildly different and working together. But let's revisit that definition. So whenever you read this, add-ons are dynamically linked shared objects written in C++, I would like to draw attention to the dynamically linked shared objects. On Windows, it essentially means a DLL. So node add-ons are just DLL. So let's just dive a bit into it. So when you require an add-on, first Node.js has different cases for the require statement. It checks that, okay, the module is extension, it's an add-on. So we need to call process DLOpen. DLOpen then calls a bunch of functions till it reaches UV DLOpen, and finally, which loads the add-on into your process using load library W. Sorry, load library EXW. So as Linus Torvalds always says, talk is cheap. Let's go to the code. So the first thing is you can print out your current Node.js's loader.js file using the first command here. It essentially just prints out the contents of the loader.js file. If you look at the second slide, and if you look at that part, it checks that, okay, this is an add-on file. Let's call it process.dlopen. DL.open, let me go there. Yeah, so DL.open calls another function called dlopen, where it does a bunch of checks, and for Windows, it essentially ends up calling this part, where there's another process called, another function called uv_dlopen, and that on the fourth bit, you can see it calls load library EXW with certain parameters. So now you can see that add-ons are loaded into your process just like any other DLL would. So let's look at the demo add-on code. Not diving too deep into it, just these are the three components first. This is C++ add-on code. It's from the wiki itself, where it just prints hello world. So this is your hello.c file. We'll dive into the details of it a bit down the road. Second thing we need to create is a binding.zip file. Think of it like as a make file but for add-ons. And finally, you need to run 3 commands where you install Node.zip, you configure it, and then you build it. You just need to do it from a Visual Studio command prompt, and at the end of it, you should have a add-on.node file. And if you load it into a P viewer, you will see that it marks it as an executable DLL. Thereby, you can confirm that, okay, this is an executable DLL. So let's dive a bit more into it. This is where I have this repository called Sinister VSIX. Here we go through the whole add-on development process, starting with a very simple Hello World extension. We look into some FFI, we write a bit of Rust code. And then we backdoor a legit extension using two methods, one where we have the source code and one where we do not. So let's look at the simple hello world task. So this, I'm not sure if it's visible, but this is a very simple hello world extension add-on shellcode. So here you have a function called run shellcode, which is your usual, hey, allocate this memory, copy your payload in here, and do this stuff. Pretty much your standard stuff. Here is something, here's a show message box code, which essentially just calls this one. And finally, we initialize the add-on, where the idea is, so in a DLL, when we have to export things. So this is a template code which says that, hey, whenever this first function, show message box with a small s, is called, call the add-on function. I really need to name my functions better. But the idea is, you have your traditional binding.zip file, you configure it, you build it, and then you call it like this. You have your usual JavaScript code to require something, you specify the full path, and then you call the function which we exported. And you should have shellcode execution. Now this particular shellcode is being run by node.exe, which is a signed process. You can even see the thread where it is being run, as well as, yeah, we can see the thread which is being run, as well as the stack. So pretty much standard stuff, not a lot of fancy stuff going there. So at this point, we can say that, okay, we wrote some C++ code, we compiled it, we made sure that we can run it from JavaScript, and we can execute shellcode using it like any other payload DLL. So at this point, when I was first developing this whole thing, the question came to my mind that, hey, why aren't we using FFI? Because Node has some nice FFI modules to it. So let's create an extension. So the quickest way to create an extension is Microsoft provides this program called YoCode. You can create a demo extension with just a single line. So that's the code for it. It creates a very basic extension for it. Now, here are certain things we need to talk about. Let's look at the package.json. First, we add the FFI RS, which is a Rust-based FFI module. We add that as a dependency. I've tried other FFI modules, which like popular ones from NAPI and stuff, but Electron 20 seems to break them. Previously, it used to work, but right now I was having a lot of trouble. So after a bit of trial and error, this is the one which seemed to work. Right. The second thing is the command key. So whenever we write an extension, we need to register a certain command, where that here, when this action happens, or whenever this command is called, you execute this. It's pretty standard stuff. So whenever our extension is called, the say hi function. Again, if this is pretty standard message box A code, what we are doing here is we are loading user 32 DLL, we are calling the message box A function from it with some of the parameters. Right. So if we write that code, we press F5, which is how you create this little window where you can debug your extensions, and launch the hello world command. We see that our extension is activated. Nice and simple, right? But let's see, where is this code coming from? Where is this thing being run from? Right. If we look at the stack behind this, we can see that this particular message box, there is something called FFI RS Win32 x64 msvc.node. Right. This another node file is responsible for somehow calling this. And if we load that up into any PE viewer, we see that, okay, this is just another .node file or another DLL. So, as Jesse Pinkman once said, we need to cut out the middleman. This is, so just a TLDR, we can always use FFI libraries like FFI-RS, but it still is compiling to a node add-on. So instead of having a middleman, let's get, I think it's better offset to just get low-level access ourselves. So this is where we start writing Rust code. But before we do that, it's very important to know what's a VSIX file. So VSIX is essentially the way extensions are packaged with all your dependencies, and it's essentially a renamed zip file. So whatever extension, whatever dependencies your module needs, it's all combined together, and we have our VSIX file. So if we unpack an extension, we'll see this is more or less the file structure. The most important thing to note here is below the extension, there's something called an out directory with extension.js. This is where the primary extension code usually lives. This will come in handy later. So we do our usual, we use the YoCode Visual Studio program to create another dummy extension. Now, here's one thing we need to do. We need to install something known as Neon CLI. Neon is a Rust program, Rust module, which allows us to interface with JavaScript in a super easy way. And we need to install VS Code's VSC package, which allows us to compile and package VS Code extensions, essentially. So what we did was we updated the package.json to include our Rust program when it builds it. So if you do a npm init neon, you will have these artifacts separately in a different package.json, but you can just take them, copy paste them into your package.json file, and what it will do is when you run vsc.package, it will compile the Rust modules, the JavaScript modules, and it will package them together in a nice little extension. So we just include all that stuff. We update the compile function in JavaScript in package.json to include our Rust stuff. We move the Rust module inside the output directory, because remember that's where the extension code will live. And finally, we just have some other dependencies here. But let's take a look at the Rust code. So this is the hello world. This is another hello function. Again, it just does your usual, hey, allocate virtual memory using virtual alloc, copy code over and execute it. But previously we had a lot of template C++ code. Here, all we need to do is we need to add this attribute macro where we are exporting this. That's it. We don't need to do anything extra. And the only thing extra is probably we need to include Neon as a dependency in our cargo.toml file. But that's it. No more C++ shenanigans. We don't need to write it from a Visual Studio developer prompt or anything. That's it. If you have some existing Rust tooling you want to port to this, you just need to add that particular line with Neon export. And how do we load this? In our demo extension, there would be a function called activate. We'll get to that later as well. And we just need to require our node add-on. You can just use dot to include everything in the current directory. And then you can call the hello function, which you define in the Rust program. And once we run vsc.package, it should compile our Rust program. It should get through. It should package the VS Code extension, and we should have a VSIX file, which we can install with code --install, and we will have that in our VS Code. And now this works. This absolutely works. Right, we have our shellcode running. You can see it's being run by code.exe. You can see our index.node file being loaded as a module. But this is very ugly. If you go back, that extension looks like nothing. No sane developer would probably install that. So this is where the next part comes in, which is how do we backdoor a legit extension. And we target Microsoft Live Preview for this because honestly, it's just fun to mess around with Microsoft. And also it's open source. So we are not violating any terms of service here. So Microsoft Live Preview, this is how it looks. If you remember from the initial slides, that this is how it looks when you just install it from the server directly. Now we have our usual Neon, we have our cargo code, but here we made one change. In the previous code, we were waiting for the thread to complete execution. This time, we won't be doing that because we don't want to obstruct the normal workflow of the extension. If a user is clicking an extension and it's not working, they will get suspicious. So we just let it run in a separate thread altogether. So next thing we need to deal with is Webpack. Now Webpack is a very useful thing for developers. I absolutely despise it because it caused me a lot of trouble. Essentially Webpack packages a bunch of things together, makes things faster on the front end, but again, it caused me a lot of trouble. So let's deal with that. So Webpack usually doesn't like add-on files. It doesn't really know how to deal with them until unless we tell them. So it needs a loader of sorts. So we tell Webpack that, hey, use native add-on loader. And that pretty much does it. Next thing we need to talk about is activation events. So every extension has a list and an array where it specifies that, hey, trigger this extension when this event happens. Those are activation events. And whenever the activation events are triggered, the activate function which we saw previously, that is the one which is called. So so just like before, whenever activation event is triggered, the activate function is called. And this time we include paths to a node file. We can call the hello function. Finally, we update package.json. You can tweak the version number. If you do not tweak the version number with the latest one, it might show some differences that, hey, update to the latest version, which you might not want to do. You need to add the native add-on loader and neon CLI in your package.json as dependencies, because remember Webpack needs it, then the Rust module needs it. And this is a very hacky solution where we copy all the requirements into our target directory. This is not really super clean, but we'll see a cleaner solution in the next task. We just update a bunch of the scripts so that we compile our Rust program, we copy it into our target directory so that when the extension is triggered, it knows where to find all the dependencies and stuff. Building is super easy, same three steps. Sorry, one step has been updated. First, we run npm install to install all our requirements. We run compile for sanity check to make sure that our stuff is compiling correctly. And then we package everything into a simple extension called, and we have liveserver.version.esix as an output, which we can install. And when we install it, somehow Microsoft doesn't check the source where it is coming from. At least it doesn't depict that in the header. And we can see that we get the same exact looking extension as we have downloaded it from the store, including the blue check mark, including the latest download counts and stars and stuff. So it's very difficult to tell whether your extensions which you have installed, have they been tampered or are they from the extension store right here. And definitely when we trigger the activation event, which in this case is previewing HTML file, we have our shellcode execution. But what happens if we do not have our source code? What do we do then? So for that example, I've taken another extension called live server. It also does similar things. But this time, even though the source code is open, we don't want to violate any terms of services, we'll treat it as a black box, that we do not know what the source code is doing behind the wall. So first thing first, you can download the VSIX format. Previously, Microsoft used to provide a button where you can click and download. But right now, you need to get a little creative where you need to use the API, which is very simple. You just take the extension, you get the developer name, and you just request the version. That's it. You unzip it to get the contents of it. And like we said, VSIX files are nothing but a zipped file. And once you unzip your target, you should have the source code for it. Once you have the source code, you can literally take the add-on which you compiled in the previous module, copy it over, add your line in require index.node.hello in the activate function. And finally, when you're done, you save your file, you should have these three files there, which correspond to the original structure which we saw of a decompiled VSIX file. And then we just zip everything together, right? And when we zip everything together, we should be able to load our extension. And again, on triggering an activation event, we should have our shellcode execution. Now, again, if you take a look at this, it's very difficult to tell whether this is coming from the store itself or is it coming from, or if it's malicious, right? So now let's talk about detections. How would you detect these? So if I'm being honest, I've not been truthful with you, there's one visual difference which is there when you install an extension using, let's say, the command line, which is this. Right under the installation page, there is one difference, whereas in the malicious extensions, it says VSIX. So if we go back a bit, if we go to the live server, yeah, this is the one which we installed from the command line. And if you can see on the right side, under the installation tab, it says that the source is a VSIX file. So that is your primary indicator that, hey, this extension, it seems like it has been tampered, it has been dropped from the floor. Now, can you maybe upload it to, let's say, OpenVSIX or VS Code Marketplace? Maybe, you never know. But that would be a violation of their terms of services and in bad faith. So we do not do that. It's really bad. So no. Now let's talk about some of the detections in IOCs. First is definitely the visual cue which we saw in the extension page. The second thing is loading a .node file in an extension itself is really malicious. Like we have difficulties with loading an unsigned DLL in the first place is malicious. So having a .node file itself is like add a layer on top of that. Finally, no developer. I don't think any single developer in this room has ever used a VSIX files directly to load an extension. So you can monitor the command line for any such events. And finally, all those detections which we have with DLLs, because again, .node files are just like DLL files. It's essentially it's similar to how we monitor a CPL file. Yes, there are specific detections for CPL files, but the detections for DLLs also apply to them. So these are some of the detections in IOCs. So how do we prevent them? So pretty simple, just prevent anybody from loading extensions from disk. Or we can do a signature check that, hey, is this extension saying who it is? You can keep a wide list of extensions from saying that, hey, developer, you can only install these extensions, or like these are the ones allowed with these hashes. And finally, which is very important, we can maintain a bill of software, because sometimes it's not the extensions which are compromised, it's the dependencies which are. The funny thing is there was this huge controversy last year about an material thin extension where the extension itself was not compromised but very obfuscated, but one of its dependencies, it got compromised and the developer was accused of supplying malware when they were in fact not doing that. So maintaining that bill of software that, okay, this extension depends on these tools and these versions, that is always helpful. So what are the improvements on these tablets? What are the things which we can do better? The first thing is we can always not ship the extension or the node add-on with the extension itself. What we can do is we can just ship the code, and during runtime we can have our payload reach out to a server, download the add-on, and then take things from there. Right, we can delay the execution to raise efforts. Those of you who have used C2, for most commercial C2s, for example, BRC4, anybody here has used BRC4? So BRC4 right now comes with something called an execution delay parameter built in. We can add those delays, we can add certain features like, hey, trigger this extension only when this particular activation event is met. So we can modify that as well. And finally, the usual JavaScript code and obfuscation and all those techniques can come through. So it's not just one detection, it's not just one improvement, it's multiple improvements. So we have, let's say, a very legit looking extension delivered through phishing mail saying that, hey, we found that this particular extension has been compromised. Why don't you install this particular version? And then you load it remotely and all that stuff. So just to give a brief recap of what we went through the history of VS Code, we saw some extensions in the wild, we touched a bit upon add-ons, and we started with a little bit of a Hello World program, and then we worked our way to building almost identical ones, and we touched upon some detections in IOCs. So the repository, the semester VSIX repository which I have, it contains most of the source code. So even if you don't follow along with this, you can always visit that repository. On the dev branch, there's also a tool which backdoors extensions automatically to you. It's in beta, so I'm still testing it out. and if these slides will also be available there. So I guess that's pretty much it. That was my talk. Anybody has any questions, any improvements, ideas? No?
Okay, so yeah, any questions from the audiences? I think so. Okay.
Thank you. I have one question.
Yeah, sure.
Thank you for your speech, talk. It's very amazing. And in addition to malicious extensions, many VS Code extensions have been reported recently with vulnerabilities. For example, this month, popular Markdown Preview Enhanced was one such example. So developers should consider security when deciding which extension to install. But I have no idea to check which extension is vulnerable or malicious. So do you know a good way to research the security limitation of VS Code extensions?
Actually, it's very difficult to verify the legitimacy or whether this extension is malware or not. So my advice is obviously maintain the bill of software. The researchers at COI, they do audits of certain extensions and they publish the malicious ones. So keeping up with their research is one very good way to check that, hey, this extension which I'm using, is it good or bad? And finally, it's usually suggested to just use trusted extensions. Like if you're downloading it from Microsoft and you're verifying it, there's a fair chance that those are not malicious, especially the ones which are published by Microsoft or other trusted platforms themselves. But again, trust right now in the security space, it's a chain. It's a chain. So you never know when something in the loop gets compromised. So that's where the bill of software comes in, that hey, this extension, these are the dependencies which it uses. Just keep a lookout that hey, this dependency is compromised. We got an alert today. Tell the developers, hey, you cannot use this anymore. So that's the only way to stay up to the game. It's a cat and mouse game.
Thank you. Yeah, I also check COI Security's blog every day. Yeah, it's very good source. Yeah.
Yes, they specialize in extensions and extension security right now. All right. Thank you.
Any other questions? We have around 4 minutes left. Yes. Okay. So one from me. Thank you very much for your awesome presentation. Actually, I love the presentation, which contains a lot of cases in the wild. So I'm very impressed for your research. And I'm just curious that the lots of mobile developers of VS extension is now switching to the JavaScript from JavaScript to the binary code usage. So, I don't know the specific about that, but I just come up that perhaps this change is made because the developer may use that VS Code extension as a model distribution for so on. So do you see any signs of this? Or just the distributed binary is just the original binary, or something similar to the existing malware?
The thing is, first thing to understand why VS Code extensions were this popularly talked about up till 2 years ago. The first time I read about them was from a blog on MVSec where they talked about this. So the reason developers started using this thing is because previously the only way people were using extensions was from Microsoft Store. Microsoft Store is very heavily monitored. Now, ever since these AI prompt editors came in, we started OpenVSX. They started attacking that. In the Solidity extensions which we saw, they were targeting these developers because cryptocurrency developers are easy targets. They have a lot of money on them. You can exfiltrate using blockchain. it's untraceable. The reason behind we are seeing more and more binary code is because obviously binary and native code is more powerful than JavaScript code, and static analyzers are getting ridiculously good. Right, they're getting like super amazing at their job, especially now that we have so much of AI integration built into them. So binaries can be a bit difficult to reverse engineer. You can obfuscate a binary in so many ways. You can use virtualization, you can use code flattening. There's much more obfuscation avenues as compared to something like JavaScript, like in JavaScript stuff. Also, another thing is Electron is also partially responsible for this, because Electron 20 broke a lot of stuff. So, a lot of malware which we were using internally, not for gaining initial access, it stopped working one day. And I was looking at like, why did it stop working out of the blue? And then we are seeing that, oh, it did not stop working. It's that how Electron treats memories or native add-ons or OS calls changed. So if you want that powerful of a obfuscation, because these shellcode loaders, if you drop them any EDR, not just EDR, Windows Defender might pick them up. So if you want some of those powerful techniques like fluctuations, memory hiding and all that, and that's a capability only native code can bring to you. So it's a mix of both your targets changing, your delivery changing, as well as defenders getting better. And another reason why we switched from C++ to Rust is because, in my experience, Rust is, okay, if somebody's looking at your code, it's already, if somebody's looking at your binary, you're already too late, you're caught. But in general, defenders are, it might be a personal bias, but defenders are better at catching C++ code because the artifacts have been there for a very long time. And Rust just adds that level of complexity in the code-wise, in the add-on, while keeping your code to a minimum. And there is a bit of a personal bias there. So that's why we are seeing the change in the threat landscape.
Ah, okay, I see. Yeah, thank you. Thank you for sharing your knowledge. Okay, so the big clap to speakers again.